Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 27, and starting this lecture we will be actually introducing some amount of modeling in terms of how does a Cryo-MOS device can be modeled so that we are able to extract the electrical characteristics of the device in an analytical sense of it. So, with this, the outline of the talk will be we need to model the Cryo-CMOS, right, within which we need to learn what is a Poisson equation and what is a Poisson-Fermi equation as related to cryogenics. We have already studied incomplete ionized dopant contribution to the Fermi level. We will carry it forward and explain how it influences the Poisson equation solutions. Also, we will be looking into the mobile carrier concentration, the meaning of that, and then verification of the Boltzmann statistics and how is it different from the Fermi statistics as we know of it. So, first let us look at the modeling of Cryo-CMOS. So, what we are trying to do is that based on first principles of physics, can we develop analytical model which is valid right from room temperature down to deep cryogenic temperatures, right. So, that is the overall sort of a global sort of approach to this problem, that how does a device behave when it shifts from room temperature, which is 300 Kelvin, to deep cryogenic temperatures. So, this is room temperature which is 300 Kelvin here, right, and when you say deep cryogenic temperatures, typically 4 to 10 Kelvin order ranges there. The physics of the device almost remain the same in this range of temperature, 4 to 10 Kelvin. So, we will not be going into various short channel effects directly, but even a long channel effect will give you an idea about what the idea is all about. So, if you look at the left hand diagram here, this one, this is a schematic of a long channel NMOS transistor, right, where if you look carefully, this is your source, let us suppose, and this is your drain, right, and this is the channel which will be there between source and drain, right. So, if you do not apply any bias Vd, source is in all respects grounded, right, and we apply a positive bias here with respect to source, then if I also model such that my drain is first of all shorted with respect to ground, then as you all know, with applied gate voltage more than the threshold voltage, an inversion layer is formed, and the thickness of the inversion layer will be constant moving from source to drain side, because there is no bias on the drain side to deplete it. However, as you start making the bias on the drain side more and more, the thickness of the inversion layer starts on decreasing as you move from source to drain, and it is eaten away by the depletion region. So, these are all basic stuff which you already possibly know by this time around. So, now let us see how does it influence the overall characteristics of the device. This is the x axis, which is basically the longitudinal direction. So, longitudinal direction is x axis and the transverse direction is basically my y axis, right. Now, two important points to note here, just do not worry about this, we will come to this later on, but typically we define a term known as surface potential, which is psi s, right, and it is basically a function of x as well as of y. And the surface potential is basically the potential at this point, which means if you put a voltmeter at the silicon dioxide interface, then the potential seen by the device is basically known as the surface potential. Now, we all know that the surface potential psi s, if it is a function of x, y, because you have applied a drain voltage at a finite VDS, right. When you have a finite VDS, psi s will be a function of s. When VDS is actually equals to 0, psi s of x will not be a function of x, right, will not be a function of x, and it will be constant. This is surface potential, and the overall potential is psi, and if you look at this is a function y which you see, right. I will again rewrite this statement for you to be clear. The general statement of potential is psi of x y, right. Now, when we go to the surface, we write psi of x as it is a function of y, and this is equals to defined as the surface potential, right, surface potential. Now, we also say that psi of s of x is constant if your VDS is 0, right, or almost 0 value. However, there will be a potential psi of y which will be actually going in the transverse direction right from silicon dioxide down below, right, and that is what it is, psi y is written here, right. we are assuming that the substrate is almost grounded, and therefore there is no body effect or back body effect available to us. What you see here is the width here, this is the width of the device, this is the length of the device from source to drain. These are my source and this is my drain, let us suppose, and I have contacts here, metal contacts, 3 metal contacts, which is designated as a source, a gate and the drain. Now let us concentrate on this curve here. This is basically the potential and the band diagram at this particular point, energy level diagram. So this is FSEA is basically the Fermi potential as you move from one side to the other side, as you go from top to bottom. In fact, as you go from top to bottom, you will see that the potential becomes constant as you move more and more towards the bottom side, right, and that has to be true also. The reason is potential is constant because there is a let us suppose you have given a fixed bias at the substrate region. So the overall potential should drop down to that in order to maintain the continuity of the potential at that region. Now we define a term here, q times psi of A, right, q times psi of A, and there is another term if you look at minus q times psi of B, right. Psi of A and psi of B are the two terms which is being mentioned here. This dotted curve which you see, this dotted curve is the intrinsic Fermi level which you see. There is a surface potential curve which is given as q times phi s, right. Then there is a Fs of EA is the Fermi potential, and 1 minus Fb of EA is basically the probability of finding holes at this lower region. This is the probability of finding electrons and this is the probability of finding the holes. The drop of psi of A is basically the difference in the potential between the intrinsic Fermi level to the conduction band edge, and psi of B is primarily from the intrinsic Fermi level down below to the valence band. So I have this conduction band here, right, I have this intrinsic band here EI, I have this valence band here, and I have an acceptor level which is kept here. So I have a p-type semiconductor and it goes up to the right. So please understand it is still not inverted. So the p-type semiconductor layer is always available. The difference between the acceptor ion concentration in the intrinsic layer is given by minus q times psi A, and q times psi B is nothing but the difference between the surface potential and the intrinsic layer concentration. So the drift diffusion model and the Poisson equations are solved using x and y in x and y direction. What is the Poisson equation? Actually, Poisson equation actually relates the electric field to a larger extent to the total amount of dopant species or total amount of charged particle available, right. That is what is Poisson equation. What is drift diffusion? Whenever you apply a bias, when the charged particles are moving under the influence of an electric field, that is basically a drift. When you have no bias applied but the charged particles are moving by virtue of concentration gradient, that is defined as diffusion. So I have a drift diffusion equation and a Poisson equation. You can go through it, the basic idea from there. Let us look at the Poisson equation, one dimensional Poisson equation, and it is given by this formula here, right, and it is given d2 psi dy 2 d2. So basically it is d of dy dou of psi dou y, right. This is what is this part about. Now this is basically the electric field in the transverse direction, right, and this is the first derivative of the electric field. So this is electric field in the transverse direction, this one, and therefore this whole quantity comes out to be dou of dou y times Ey. So this relates to you what, how the electric field is varying in the y direction to the total amount of charge available, where the number of, I am putting a minus sign in the outside. So I have a number, because electron is a negative charge, I put minus, I put a positive charge p here, and I am assuming that acceptor ion concentrations have accepted electrons and thereby converting them into free holes. Q is the elementary charge and psi is the silicon permittivity. Now the potential which you define basically by my previous lecture, you must have also seen, is that psi is equals to the difference of the Fermi level and the intrinsic layer divided by q. So I get psi equals to approximately equals to EF minus EI by q. EI is the intrinsic layer and EF is the Fermi level, right. More is the difference between EF and EI, obviously more will be the potential which you will get, right. Okay. Now, so this Poisson Fermi equation relates two things, on the one side an electric field, on the other side the total charge at a particular point. Now, as I discussed with you, there are three terms effectively on the right hand side. The first term represents the electron concentration, as I told you. this represents, so this is a free electron concentration, free electron, this represents free hole, and this represents the ionized dopant species, right, ionized dopant. This is where in cryogenics makes a difference. Till now, if you remember correctly, we are assuming for all 300 Kelvin calculations that I do 100% ionization, and therefore I know what is the value of Na minus. But in most of the cases this might not be true, you might not have 100% ionization, and therefore Na minus will not be exactly equal to that of the total number of charged particle present. Now that is what I was coming to, you see. So I have an incomplete ionized dopant species here. If I assume that the thermal equilibrium is applicable to all the carrier concentrations, then if you look at the first statement, that at room temperature, at both room temperature and cryogenic, which means that both at around 300 K and 10 K, let us suppose, the majority carrier concentrate can deviate from the implanted doping profile. So, if you do a implantation, say you are doing a Gaussian implantation, and if I am assuming that the implantation is proper, annealing is proper, we still get a deviation between the number of acceptor or donor species inserted into an intrinsic semiconductor and the total number of electrons available. However, please understand, electrical neutrality is never violated. So, electrical neutrality will always be maintained, and that is purpose it is known as an incomplete ionized dopant species, or dopant, or maybe an acceptor species as well. Either of the two I can say to be true. Now, and that is what I have discussed in our earlier discussion, again I am repeating it. So, at cryogenic temperatures there will be heavy incomplete ionization is relatively strong, and therefore this leads to what is known as a carrier freeze out. So, you will have carrier freeze out at exceptionally low temperature, right. So, it will carrier freeze out at low temperature at around 4 Kelvin. At 4 Kelvin also the contribution from thermal dopant is very, very low, because in any way your energy is so low. If you remember, my kT by Q at 300 Kelvin is, which is thermal equivalent voltage, is approximately 25 milli electron volt, right. At T equals to say around 4 Kelvin, there will be an 2 order decrement in the value of your thermal energy, and therefore that might be enough to generate large amount of ionization. As I discussed with you, field assisted ionization is also available, and which influences the concentration in a bulk MOSFET operation, especially in the cryogenic region, right. And that's what as a you should know. Therefore, two aspects which contribute to the right hand side of the Poisson equation. If you look at the Poisson equation here, this one, then the right hand side contribution comes from two things. One is ionization, right, which can be thermal and it can be field assisted. Then you have this, which is this part, and these are free electrons and holes which are available to the device. So, the total number of free charge carriers are shown here. Okay. Now, we discussed this part, incomplete ionization. Now, let us come to the validity of Maxwell's Boltzmann approximation at relatively low temperatures. So, the MB distribution or Maxwell's Boltzmann's approximation at deep cryogenic is still a matter of study, and there is a large number of studies available to us. However, that it has come to the mind, or it has come to overall community, those who are working in cryogenics, that extremely at deep cryogenic, the semiconductor actually becomes strongly degenerate. Strongly degenerate primarily means that there might be a case where the Fermi level is actually going inside the conduction band, and therefore the loss which you get by virtue of reduced value of carrier is slightly made up with the strong degeneracy of computer. And that is the reason at very, very low temperatures, Maxwell's Boltzmann approximation is not valid for any of the devices, right, and you still do into Fermi-Dirac statistics. However, and this is a point slightly on the research oriented side, those who are interested, at 0 Kelvin, right, at the 0 Kelvin there is the contradiction, right. We are not able to understand whether it will be a Maxwell's Boltzmann or Fermi-Dirac. However, practically speaking, 0 Kelvin limit can never be reached to a larger extent. So, absolute 0 conditions are almost impossible in the current scenario, right. So, what we need to verify therefore is that if even to what extent in deep cryogenics the Maxwell's Boltzmann equation are holding good, that you need to find out in a general sense. So, in order to do that, we do a numerical calculation of equilibrium Fermi level. I will explain to you what do I mean by equilibrium Fermi level. I had already told to you what is a Fermi level, right? What do you mean by equilibrium Fermi level is that when there is a dopant species and you connect say a p-type material with n-type material, right, the electrons from a region of higher concentration will flow to a region of lower concentration, and as a result there will be a depletion region that just happens in a p-n junction diode, correct. But you need to ensure that for a stable current flow between point A and point B of any junction, the equilibrium value of the Fermi level should be a function of x, which means that if the Fermi level is perfectly aligned and straight, there will be no net flow of charge carriers, whereas if the Fermi level, equilibrium Fermi level makes a change slightly top or bottom, I would expect to see a change in the numerical calculation which we see in case of finding out the Fermi level. Equilibrium Fermi level primarily means that if I assume that the net charge movement from left to right and right to left are exactly the same, I say that the equilibrium Fermi level has been maintained. It is almost a straight line which is maintained. Now, computationally, those who work in cryogenics, they have seen the equilibrium Fermi level is actually numerically calculated down to approximately 100 millikelvin. And the option or the reason why do you want to go for 100 millikelvin is that all your qubits are somewhere in the millikelvin region, right? And therefore, the first part of the readout circuitry is almost closer to the 100 millikelvin, and therefore, the variation of Fermi level at 100 millikelvin is an important part. How is it done? You do a standard Fermi-Dirac statistics, you maintain charge neutrality. So, you take a Poisson equation, you maintain a charge neutrality, and then you ensure that the number of holes available is exactly equals to the ionized acceptor concentration Na minus, right. Now, what we do is that we go on changing the temperature, and for each temperature and doping concentration value, we try to find out an implicit relationship of EF with respect to various parameters within the system, right. So, the idea is try to find the value of EF, which is the Fermi level, at various points, and these are numerically solved and analytically expressed. Plug in the value of temperature and doping concentration, and you start getting a fresh value of EF. And this fresh value of EF which you get will be helpful for you to actually design the variation of the charge carriers as you do when you actually match two elements. So, let us suppose you take a MOSFET, you apply a positive bias on the drain side. Since the electrons are flowing, the Fermi level will not be same across X, and therefore, Fermi level change will be seen. So, what we try to find out when we try to find out the current is, can we extract analytically dEF of X dx. If you are able to extract this information, then you know how the Fermi level is varying with respect to X, and from here you can actually calculate the value of current flowing through the device. So, this is a basic model which we do. Now, let us look at the behavior of Fermi level at low temperature. When we say low temperature, we are going from 77 Kelvin to approximately 4.2 Kelvin. On the left hand side, the y axis, it is basically the difference between the Fermi level and the valence band, and on the x axis you have the temperature. Look at this green curve or the green dotted line here and the blue dotted line at this particular point. Okay. And these arrowheads which you see, these expressions or arrowheads which you see are primarily the variation of the difference between the EF and EV with respect to temperature. Quite interestingly, and this is but obvious, and you can appreciate that at this particular point of time, that as the temperature goes on increasing, you see all of these curves which you see. So, there are two curves here. One is the dotted curves which you see, these ones, right, and one you have a continuous curves which are these ones, right, this continuous curve. So, continuous curves are primarily for incomplete ionization, and dotted curves are for complete ionization. So, let us take up a complete ionization picture. As you can see, if we take this one, let us suppose, right, if we take the first curve here and we compare that with this, let us see how it works. If it is a complete ionization, I see as the temperature starts to increase, the difference between the Fermi level and the valence band starts to become larger and larger, right, and it increases almost sort of exponentially, if not more than that. It increases in a very large fashion for a fixed value of Na, where Na is basically the acceptor ion concentration. So this curve is for incomplete ionization, and this is for complete ionization, and the difference in the Fermi level is larger in case of incomplete ionization as compared to in case of a complete ionization. So this is Na equals to 10 to the power 12, and this is N equals to 10 to the power 12. So we compared this with this. Now I have 10 to the power 18 and I have a 10 to the power 18 here. For complete ionization, this is shown here, right? And that's interesting that they go on increasing above. Now as you can see here, that at 120 Kelvin, 120 Kelvin is, this is the point at 120 Kelvin, the Fermi level EF, right, which you have found out, remains above the valence band edge with the offset greater to approximately 3 kT, right. So which means that if you dope with boron in 4 into 10 to the power 18 number of species per centimeter cube, typically at 120 Kelvin the Fermi level lies approximately 3 kT above the baseline. Now this can only be predicted if you assume that incomplete ionization has taken place, because the number of charge carriers which contribute to the movement of the Fermi level are relatively small in this case. So the behavior is therefore correctly predicted only when we have incomplete ionization is included, and therefore as you can see here, this incomplete ionization included. Now whenever you have complete ionization, which means the degeneracy is approximately equals to 0, that cannot predict to you an offset of 3 kT for Na equals to this much. Offset of 3 kT means if this is your valence band shell, and if you did have complete ionization, the Fermi level will be actually almost coincident on the valence band. But even at 120 Kelvin, where we assume that there is incomplete ionization, there is actually a 3 kT distance or a potential drop between the value of Ea and Ev, right. And this more so therefore corroborates the fact that there is always incomplete ionization at 120 Kelvin, and that is what is actually shown by the last statement here, right, specifically for 10 to the power 18, right, 10 to the power 18, we see that this is there in that sense. So that is what you need to understand, at least from the Boltzmann statistics. Now let us look at the impact of incomplete ionization. Now what does incomplete ionization do? That it allows you to have a non-degenerate semiconductor even at 100 millikelvin to as low as 100 millikelvin. Near 0 Kelvin, right, the Fermi level actually saturates to approximately Ea by Ev minus 2 for all doping level, and this corresponds to 0 Kelvin limit. So just to recapitulate the first two lines for you, primarily at 0 Kelvin the Fermi level becomes almost of the order of Fermi level approaches Ea minus Ev by 2, that we have already discussed in our previous discussions or previous talks. And this can be only possible provided you have a non-degenerate semiconductor. If it would have been fully degenerate semiconductor, the Fermi level would have actually gone inside the conduction band or the valence band for all practical purposes. And that is the reason this difference actually corroborates that you will always have a non-degenerate semiconductor at Kelvin, and that is purely because you have a sort of incomplete ionization. There is another technique, that whole expression from Maxwell's Boltzmann equation is coming out like this. This is E suffix x, this is E suffix v, which you did. Now if you substitute the charge neutrality equation and assume that number of holes in p-type material is exactly equals to the number of ionized atoms, then I get this as the final expression here, that is, it is quadratic in nature, exponential Ev minus Ef by kT, which you get, right, and then that gives you the value of the charge neutrality condition. Now how do you verify Boltzmann statistics? If you solve for Ef minus Ev, I will get this expression here. Now in this case, if you t tends to 0, if you do limiting t tends to 0, you see I get Ef is equals to Ev plus Ea minus Ev by 2. This I was talking about you, right. This is Ea minus Ev by 2 which you get, and this is the valence. So basically my Fermi level, if this is my Ev and this is my Ea, let us suppose this is my Ea, then somewhere in the middle of the two I will get Ea plus Ev by 2. So this will be Ea minus Ev by 2. So, this is in energy scale, this is EV plus EA minus EV by 2. So, this is the energy scale which you get, right, for limiting case at t equals to 0. So, just to therefore recapitulate what we did in this lecture, we try to find out the Maxwell-Boltzmann statistics, right. Using that, we try to show you that degeneracy is not set in, right, and therefore there is a 3 kT offset at even t equals to 0 Kelvin. Then we do FD and find out the Poisson equation, right. In the Poisson equations, we try to find out relate electric field as a function of the charge which you are there, net charge which is available to you. We also saw that how does EA minus EV varies with temperature and doping concentration ND, and this gives you a brief idea therefore that when you start modeling, you need to ensure that non-degeneracy is already available to you, right. So, with this, let me close the discussion which you have, and I hope you learned something new in this lecture, and hope to meet you soon. Thank you.